Welcome to this lecture on the Hall effect. This is a fundamental phenomenon in condensed matter physics that allows us to determine the type and density of charge carriers in a conducting material using just a magnetic field and some electrical measurements. By the end of this section, you'll understand how charge carriers respond to magnetic forces and how we can use that response to probe the microscopic properties of materials. Here's how the Hall effect works in detail. When current flows through a metal slab and a magnetic field is applied perpendicular to that current, the moving charge carriers, typically electrons, experience a Lorentz force. This force pushes them toward one side of the conductor. Electrons accumulate on one surface, leaving a deficit of electrons, or positive charge, on the opposite surface. This charge separation creates an electric field across the material, which we call the Hall field. At equilibrium, the electric force from this Hall field exactly balances the magnetic force, so electrons stop accumulating. The voltage we measure across the material is the Hall voltage, and it depends on the current, the magnetic field strength, the thickness of the material, and, crucially, the density of charge carriers. This relationship, VH equals B times I times D divided by N times E times T, is the key to extracting information about the material's microscopic structure. The current balance is an instrument designed to accomplish three key objectives. First, it measures the actual size of current flowing through a conductor. Second, it determines the magnetic flux density, that's the strength of the magnetic field, inside a solenoid or at the center of a circular coil near a straight wire. Third, it investigates how different factors affect the magnetic force on a current-carrying conductor. This connects directly to the fundamental equation F equals BIL sine theta, where the force depends on the magnetic field strength, the current, the length of the conductor, and the angle between them. The current balance apparatus has a specific design. It consists of a horizontal metal wire frame, labeled PQRT, that's pivoted about a horizontal axis called XY. This frame sits inside a solenoid with a known number of turns per meter. The frame is suspended from a knife edge, which acts as the pivot point. A mass can be hung from the frame to balance against the magnetic force that develops when current flows. This elegant setup allows us to measure the magnetic force by determining what mass is needed to restore equilibrium when the current is switched on. Current balance is a fundamental concept in electromagnetism. It occurs when a current-carrying conductor is placed in a magnetic field and reaches equilibrium, meaning the magnetic forces acting on opposite sides are perfectly balanced. Think of it like a seesaw. When the forces on both ends are equal, the beam stays level. In this case, the current is determined by analyzing the equilibrium condition. The magnetic force on one segment, labeled RT, equals the magnetic force on the other segment, XY. This principle is expressed mathematically as I1L1B equals I2L2B, where I is current, L is length, and B is the magnetic field strength. This method is considered absolute for determining current values based on fundamental physical quantities. We've covered the fundamentals of electromagnetic induction. Now let's explore back EMF and self-induction, concepts that explain what happens when current changes in a coil. When mechanical energy converts to electrical energy and then to heat energy in a galvanometer, we're seeing energy transformation in action. There are two main types of electromagnetic induction: self-induction, where a changing current in a coil induces an EMF in that same coil, and mutual induction, where current change in one coil affects another nearby coil. Let's focus on self-induction first. When a switch closes in a circuit with a coil, something interesting happens. Current doesn't instantly reach its steady value. Instead, it grows rapidly, and during that growth, a large back EMF appears in the coil. This back EMF opposes the current that's creating it, which is why we call it back EMF. The magnitude of this back EMF is directly proportional to how fast the current is changing. Mathematically, we write this as EB equals negative L times DI over dt, where L is the self-inductance measured in henries. The negative sign reflects Lenz's law. The induced EMF always opposes the change causing it. Self-inductance is simply the coil's ability to generate its own EMF when current through it changes. Self-induction is fundamentally an electromagnetic phenomenon where a changing current in a coil induces an EMF within that same coil. Think of it as analogous to photosynthesis, a process that feeds back on itself. When you first close a switch, current doesn't jump instantly to its final value. Instead, as current begins to grow, the changing magnetic field it creates induces a back EMF that resists that very growth. This is nature's way of opposing sudden changes. The faster the current changes, the larger the back EMF. This relationship, that back EMF equals negative L times the rate of current change, is the mathematical heart of self-induction, where L captures each coil's unique ability to generate this opposing EMF. In a practical circuit with a coil, resistor, and switch, the self-induction effect becomes very clear. Before the switch closes, there's no current. The moment you close it, current tries to grow, but the coil fights back by generating a back EMF proportional to how fast the current is changing. This is captured by the equation EB equals negative L di dt. The constant L, measured in henries, is the self-inductance. It quantifies how strongly the coil opposes current changes. A larger inductance means a stronger back EMF for the same rate of change. The negative sign ensures the back EMF always opposes the change, consistent with Lenz's law. This opposition is why inductors smooth out sudden current changes in circuits. Mutual induction occurs when a changing current in one coil induces an EMF in a nearby coil through their magnetic coupling. Here's how it works. When the switch K closes, current in the primary coil grows rapidly, creating an expanding magnetic field. This changing field links to the secondary coil, inducing an EMF there. That's why the bulb flashes briefly. The induced EMF depends on how fast the current changes, expressed as E equals negative M times di over dt, where M is the mutual inductance. For continuous lighting, we'd use AC current instead, which provides constant change and keeps the bulb lit throughout the cycle. Mutual induction is the phenomenon where a changing current in one coil generates an induced electromotive force, or EMF, in a nearby coil. The key relationship is that the induced EMF in the secondary coil is proportional to the rate of change of current in the primary coil. The proportionality constant is called the mutual inductance coefficient, measured in henries. This is the foundation of transformers and many other electromagnetic devices we use every day. The mutual inductance M quantifies how effectively the magnetic field from one coil links with the turns of another coil. Mathematically, the magnetic flux through the secondary coil due to current in the primary is phi12 equals M times I1. Rearranging, mutual inductance equals the flux linkage per unit current. Importantly, M depends entirely on the physical geometry, the number of turns in each coil, their cross-sectional areas, the distance between them, and how they're oriented relative to each other. M does not depend on the magnitude of the current itself. One of the most elegant properties of mutual inductance is its reciprocity. If a current in coil 1 creates flex linkage in coil 2, then an equal current in coil 2 creates the same flex linkage in coil 1. In other words, M12 equals M21. This symmetry holds regardless of the coil sizes or turns. It's a consequence of the underlying physics. This reciprocal property is crucial for understanding how transformers work bidirectionally and is fundamental to many electromagnetic applications. When current in the primary coil changes with time, it creates a time-varying magnetic field. This changing field induces an EMF in the secondary coil given by epsilon2 equals negative M times di1 over dt. The magnitude of the induced EMF depends on how fast the current is changing. A rapid change produces a larger EMF. The negative sign reflects Lenz's law. The induced EMF always opposes the change that caused it. If the primary current is increasing, the induced EMF in the secondary will try to create a magnetic field opposing that increase. The coupling coefficient K measures how effectively the magnetic field from one coil links with the other. It's defined as M divided by the square root of the product of the two self-inductances. The coupling coefficient ranges from 0 to 1. A value of K equals 1 means perfect coupling. All the flux from one coil links the other, which happens when coils are tightly wound on the same iron core. A value near 0 means poor coupling, as when coils are far apart or poorly aligned. Real transformers typically achieve coupling coefficients between 0.95 and 0.99, which is why they're so efficient. The transformer is the most practical application of mutual induction. In an ideal transformer, the voltage ratio between secondary and primary equals the turns ratio. V2 over V1 equals N2 over N1. If the secondary has more turns than the primary, the voltage steps up, useful for long-distance power transmission. If it has fewer turns, the voltage steps down, useful for household appliances. Simultaneously, the current ratio is inverted. The current in the primary divided by the current in the secondary equals the turns ratio. This ensures power is conserved. V1I1 equals V2I2. An ideal transformer conserves power. The power delivered to the primary coil equals the power delivered by the secondary coil. This is expressed as V1 times I1 equals V2 times I2. This conservation principle explains why transformers can step up voltage only by stepping down current proportionally and vice versa. In practice, real transformers have losses due to resistance in the windings and hysteresis in the core material, so the output power is slightly less than the input power. However, modern transformers achieve efficiencies exceeding 99%, making them remarkably effective devices. It's important to distinguish between self-inductance and mutual inductance. Self-inductance, L, describes how a coil's own changing current induces an EMF within that same coil. Mutual inductance, M, describes how a changing current in one coil induces an EMF in a different, nearby coil. Both follow the same mathematical form. The induced EMF is proportional to the rate of change of current, but they arise from different physical situations. Self-inductance depends only on the geometry of a single coil, while mutual inductance depends on the geometry of both coils and their spatial relationship. When two coils carry current simultaneously, the total magnetic energy stored in the system has three components. The first term, 1/2 L1 times I1 squared, is the self-energy of the first coil. The second term, 1/2 L2 times I2 squared, is the self-energy of the second coil. The third term, M times I1 times I2, is the interaction energy, the energy stored in the mutual magnetic field. This interaction term can be positive or negative depending on whether the currents flow in the same or opposite directions relative to the coil orientations. This interaction energy is what enables energy transfer between coils in transformers. Mutual induction is the principle behind numerous everyday technologies. Power transformers step voltage up or down in electrical grids and household appliances. Induction motors use mutual inductance between the stator and rotor to create rotating magnetic fields that drive mechanical motion. Wireless charging systems use mutual induction to transfer energy from a charging pad to a device without physical contact. Electromagnetic brakes use the induced currents in conductors to create braking forces. Understanding mutual induction is essential for anyone working with electrical systems, power electronics, or electromagnetic devices. The mutual inductance between two coils depends on several geometric and material factors. First, M is proportional to the product of the number of turns in each coil. More turns mean stronger magnetic coupling. Second, M increases with the cross-sectional area of the coils. Larger coils link more flux. Third, M decreases with the distance between coils. Separation weakens the magnetic coupling. Fourth, M increases with the permeability of the core material. Iron cores provide much stronger coupling than air cores because iron concentrates and amplifies the magnetic field. Engineers optimize these factors to achieve the desired mutual inductance for specific applications. In real transformers, not all magnetic flux from the primary coil links with the secondary coil. Some flux lines escape without linking the secondary. This is called leakage flux. The inductance associated with leakage flux is called leakage inductance. Leakage inductance reduces the effective coupling coefficient and causes voltage regulation problems. The secondary voltage drops more significantly when current is drawn. Additionally, real transformers experience core losses due to hysteresis and eddy currents in the iron core, and copper losses due to resistance in the windings. These losses convert some electrical energy into heat, reducing overall efficiency. Transformer design involves careful optimization to minimize these losses while maintaining adequate mutual inductance. In AC circuits, mutual inductance creates phase relationships between primary and secondary voltages and currents. When a sinusoidal current flows through the primary coil, the rate of change of current is maximum when the current passes through zero, and zero when the current reaches its peak. This means the induced EMF in the secondary is 90 degrees out of phase with the primary current. For a sinusoidal primary current with amplitude I0 and angular frequency omega, the induced EMF amplitude in the secondary is m times omega times I0. This frequency dependence is why transformers work well at power line frequencies, like 50 or 60 Hz, but their behavior changes significantly at different frequencies. The complete behavior of mutually coupled coils is described by a system of coupled differential equations. In the primary circuit, the applied voltage equals the sum of the voltage drop across resistance, the self-induced voltage, and the mutual induced voltage from the secondary. In the secondary circuit, the sum of the resistance drop, self-induced voltage, and mutual induced voltage must equal zero if the secondary is open-circuited. When the secondary is loaded, an additional term for the load impedance appears. Solving these coupled equations requires careful algebraic manipulation and often benefits from Laplace transform techniques or phasor analysis in AC circuits. These equations form the foundation for transformer design and analysis. Mutual induction is one of the most important concepts in electromagnetism. The mutual inductance coefficient M quantifies how effectively one coil's magnetic field couples with another. The induced EMF depends on the rate of change of current, not the current itself. The reciprocal property ensures symmetry in electromagnetic coupling. The coupling coefficient tells us the efficiency of that coupling. And transformers, perhaps the most important application, rely entirely on mutual induction to transfer electrical energy between circuits at different voltage levels. Understanding these principles is essential for anyone working with electrical power, electronics, or electromagnetic systems.